All right, hey guys, this is the last lesson here before spring break. We only have a few lessons left remaining for the year, and we can start reviewing. So when we come back from spring break after next week, we'll probably be in a pretty good spot to make sure we get everything done before that test starts and give us plenty of time to review. So mainly this is a lot of review stuff, so stuff that we already talked about. So you notice here the first thing that they're talking about is particle motion. So there's three things to keep in mind. The integral from a to b, v of t dt would be p of b minus p of a, where v of t represents velocity and p of t represents the position. So that leads us to two things. The first is that the integral from a to b of v of t is equal to the net distance the particle travels on the interval from a to b. And that's only true really if v of t is greater than 0. So remember, net distance is really talking about if you start at a certain position, you can change directions however many times you want to. We're talking about how much do you go from the beginning to where you end up at, and the changing directions really doesn't matter. So if you don't change directions at all, if you go in one direction the entire time, which is what this is talking about, v of t being greater than 0, just remember that the net distance is equal to the total distance. So that leads us to number 3, which is the total distance, which is the integral from a to b of the absolute value of v of t, just meaning distance is always a positive number. So total distance traveled, if I do change directions, I would have to split up our intervals. So like if I change directions from 0 to 10 at 5, I'll have to find the distance that I traveled from 0 to 5, and then also find the distance that I traveled from 5 to 10, and then really add those together. So we're looking at a couple of examples here with on our notes, and this one's kind of very similar to what we did in our last section as well. Right here we have an equation that represents our velocity, which is 3t squared plus 6. And they're talking about, hey, if the position of your particle at t equals 4 is this, then what is your position at t equals 2? So we're going to set up a definite integral problem where we're looking at the integral from 2 to 4 of our function, and that would be equal to, since this is velocity, the antiderivative of the velocity is the position, p of 4 minus p of 2. So the one thing that we are solving for in here that we need to find is p of 2, which we don't know. I know p of 4 is 72 because that's given. When I actually find the antiderivative of 3t squared plus 6t, I can then evaluate to figure out that total amount, which ends up being 68. So then you're just left with the simple equation: 68 is equal to 72 minus p of 2, which we can then then solve. B, what is the total distance? B, total distance going from 0 to 7. So if we think about that particle or that equation, 3t squared plus 6, that is not going to change directions because that is always positive, 3t squared plus 6. No matter what number you plug in for t, it always is going to be positive no matter what. So the only way that it would change directions if the velocity ends up being a negative number, which means that it does cross the x-axis, which in that case it would not. So in this case, we don't have to really account for change of directions at all. So I can just find the antiderivative, which is t cubed plus 6t, and then I plug in my integral limits, and there is my total distance, and it is a positive number, 385. Here on the next page, look, this is pretty much the same problem as before. The big problem, or the biggest change with this one, is that this velocity function right here, when you actually go to try to find the antiderivative of that, we do not have a way through calc means to find the antiderivative of this. Yeah, buddy? Are you all done? Hold on, we got a quick break here. Here, buddy. Here. Okay? You want to watch what? Hold on, we're doing a quick trying to figure out a video.
He's telling Magenta how she feels.
There you go. Blaze and the Monster Machines. All right, sorry. So with this one right here, the main thing is when we actually go to find what the antiderivative of this is, you can't do this through calc means. So you're going to have to use a graphing calculator. So with the graphing calculator, there is a way when you go to type in the math functions and calculus on those TI-83s or TI-84s that you can find the antiderivative from one value to another. So you're going to have to use that. And I'll probably share a calculator that I can find online as well so you can actually do this. But the main idea is I need to find what this answer is. So that way all I have to do is then solve for P of 3.5, which is what they did. B, what is the total distance? The total distance, looking at it as well. Let's see. This is all ends up being positive anyway. So once again, just kind of using our formula, we get the total distance is 913. Here, this question, this is pretty similar to what we did in the last unit as well. We have the graph of the velocity that is shown. Then we have a little bit of information that says that the position at t equals 8 is 12, so we know that p of 8 is equal to 12. So if it's asking for the position at t equals 3 and you know the velocity, it's always a good idea to use the definite integral going from the unknown value of t to a value of t that you actually know. So that's why they chose to go from 3 to 8. So that right there, we could actually evaluate what this is based on the fact that this is the area underneath the curve of v of t from 3 to 8. So here's our graph of v of t. So I'm going to find the area of that shaded region from 3 to 8. We got a trapezoid, or you can think of it as a rectangle, a triangle, and a triangle. And just remember that this area underneath the x-axis is going to be negative, which is what they ended up doing. So there is the area underneath the curve, and then they subtracted 12 from both sides and then divided both sides by -1 just to get p of 3 by itself, which ends up being 4 feet. B, what is the acceleration when t equals 5? If I have the velocity function, I know that the derivative of the velocity is the acceleration. So the acceleration at 5 would be the slope of the tangent line of your velocity function at 5. So if I go to 5 right here, the slope of a tangent line of a linear equation is basically the slope of this line right here. So the slope of this line, let's see, we're going down 5 to the right to -5 halves. Let me scroll up a little bit. I don't know why it's doing that. C, what is the net distance? The particle travels from 0 to 10. So the net distance would be the integral from 0 to 10 of v of t dt. So the only way we can evaluate that is finding the area underneath the curve from 0 to 10, which is 16. When you go through and you find the area of all of those shapes and then add them together. D, what is the total distance? So the total distance just means that we actually have to make sure that we use the absolute value. So it doesn't matter whether it's above the x-axis or below the x-axis. All of our areas are going to end up being positive because there is our total distance is 24 feet. When we add up the area of this first shape plus the triangle that's underneath the x-axis, ends up being 24. So one thing to keep in mind here, since this is a velocity function, the graph of it, it would change directions at t equals 6 because it goes from positive to negative. This last page here is just a good review of Riemann sums again. So the first question, A, what is the value of the integral from 0 to 18 of v of t, which is the table, represents the total distance the particle moves from t equals 0 to t equals 18, because the velocity is always positive. Okay, if I'm looking at my velocity, we have all positive values up here. It doesn't matter that it goes from increasing to decreasing or anything like that. We're just, but my positive or my velocity numbers for all of those y values are all positive. B, just using a left-hand Riemann sum of 6 subintervals of equal length, estimate what the actual the integral from 0 to 18 of v of t would be. So you can break this apart, 0 to 3, there's one interval, 3 to 6, 6 to 9, 9 to 12, 12 to 15, and then 12 to, and 15 to 18. And we just have to make sure that we find the height of all of those rectangles by the left-hand part. So that's why it's 2.3, 2.7, 2, 1.31, and 1.7, because we're finding the area of those rectangles from the left-hand side. C, same thing, but it looks like on the right. So all of your rectangles are found by the right. D, 3 subintervals, but using midpoints. So it's the middle value. So if I'm going from 0 to 6, as my rectangle being 6 units wide, I would have to use 3 because that's in the middle to find out the height of the rectangle. Excuse me. Trapezoidal sum, same as it was before. And then F, find the average acceleration. So average acceleration is always found by using the velocity function. So the average acceleration just in general is v of a minus v of b over a minus b. So in this case, we're going 3 and 9. So v of 3 minus v of 9 over 3 minus 9. And we get our average acceleration. So the second question, for what value of t in the table is the average acceleration approximately equal to v prime of t? So it says there the mean value theorem, which is one of the theorems that we talked about in the last unit before spring break, guarantees that a value exists between t equals 3 and t equals 9, such that v prime, the slope of the tangent line, the instantaneous acceleration, would equal the average acceleration is at t equals 6. All right. So that's it. This was the last thing here before spring break. I hope you guys enjoyed next week off. Try to relax, stay safe. Looks like it's going to be nice here next couple of days. So get outside, do something, but make sure you're staying safe and following the guidelines of what we're supposed to be doing. So that's it. I'll see you guys after spring break's over.